Okay, I think that will be helpful for everybody. Next Thursday is exam 2, and it's on chapters 4, 5, and 6. So there's going to be a bonus point opportunity for exam 2. Y'all want to know what it is? I'm sure you do. Let me share my screen. It's right here. It's this worksheet. Okay. So we talked about last week the 5 initial classifications for chemical reactions. That's the ones we just named. Today, we're going to talk about 3 more ways to classify chemical reactions. And so once we finish lecture today, you'll have all the tools you need to complete this worksheet. There's 15 reactions that they are not balanced. So you do need to balance them, and then you need to classify them. And I'll give you a heads up. There's often you can classify them as more than one way. Like you could classify it maybe as an acid-base reaction and a double displacement, for example, okay? So I'm just saying, if you can classify it both ways after we finish lecture today, please do so. And then you will upload this. This is actually already posted as a new discussion thread on Blackboard. Okay, so you go to Blackboard, click on discussions, you'll see the new thread, you download this worksheet, print it out, please, and work it, okay? Balance it, work together with groups of friends if you want. I don't care, do it on your own if you want. Reach out to me with questions if you want. And you have until next Monday to upload this, because we are gonna go over the answers next Tuesday. And that is the 9th, I believe. So upload it by the 8th. Anything uploaded after the 8th will not be given credit for bonus points. And then we'll go over the questions on Tuesday. Okay, I'm getting something in the chat. If you're having issues with Zoom, thank you for letting me know. Very, very sorry. I understand. Okay, so anyways, any questions on this right now? You can literally go download it off Blackboard right now. So,
when did you say that was due?
Please upload this by the 8th. And that is on the discussion thread. Okay, so if you don't want to write that down and memorize it, when you go read the discussion thread with the instructions there, it tells you make sure you upload it by that's the end of next Monday, because we're going to go over the answers and I'll post a key next Tuesday. All right, so there's that.
I have a question about that.
Yes, another question,
okay, so,
Danielle.
So like say we only get like half of them right. How many points are you giving for like the bonus of it?
That's another thing I mentioned on the discussion thread. I'm going to selectively grade this. So I'm going to I don't know exactly how many I'll pick. I may only pick 5 particular reactions, and that doesn't seem fair, I know, but grading all 15 with mega accuracy for scrutiny and all that, that would take a long time. So I'm going to probably hand select, somewhere around 5 and look at those and spot check. So please give your best effort, because you don't know which 5 I'm going to pick. Okay. I know that's probably not what you wanted. But please, balance them correctly and classify them correctly. And again, you can use me as a resource. Reach out. We'll talk about any of them if you want to. Work with friends. Don't do this on your own. So anyways, you have a whole week to do it. Well, a little less than a week, but that is listed on the discussion thread as well. I state that. So, okay. Any other questions?
So the exam 2 is on the 11th?
Yep, March 11th. Okay, other things for this week, your lab, chemical reactions lab, if you have not completed it, that's due Friday, and your chapter 5 homework is also due Friday, end of the day, okay? If you have questions on that stuff, go ahead and look at it. Please don't wait and email me, because Friday afternoons, I'm off email for the week, okay, or the weekend. But I want to be available. I have office hours. Nobody showed up today, but remember, I have office hours Tuesday, Thursdays at 9:30 to 10:30, okay? Is there Zoom lab this Friday? Yes, there is. This week, Thursday and Friday, we are starting the mole calculations lab. So that's what we're going to get into Thursday with lecture, chapter 6 stuff, and we'll do the mole calculations lab on Thursday, Friday. But please don't download that and start it right now. I have some instructions for that. I don't want to overwhelm everybody with too much info, so wait till tomorrow, and I will send directives about the mole calculations lab tomorrow. Okay, let's finish chapter 5 today. Great question, Bailey. Okay, let's get into some lecture stuff. So let me share my screen. Really quick, before we do jump really hard into chapter 5, I want to slide over here to chapter 4. Okay. And we talked about, if you remember, polar molecules. Okay. But this was at the very end of lecture, and your brain was probably fried at this time, and it was last few minutes. And I don't know, sometimes it's really hard for me to gauge if I'm moving at a decent pace or if I'm moving too fast. I get it. A lot of times people don't want to be the person to say, hey, slow down on Zoom. And I can only see 10 of your faces or so at a time. And so it's very hard for me to judge how things are going from your end. So people actually today in the 8 a.m., they started using those little emoji reactions. Do y'all see like the thumbs up, thumbs down? I'm going to ask you guys to do that periodically throughout the day. That's going to help me. But anyways, polar molecules. I'm going to remind you of a couple of things. We're going to do one poll question as a little review, and then we'll go back to chapter 5. So we said when you have polar molecules, the way you judge that is you need to ask 3 things. Does your molecule have any polar bonds? Does it have any lone pairs? And then consider the shape. Okay, we looked at water molecule as an example. We said the bonds in a water molecule are polar, plus water molecule has lone pairs. And so you could draw this dipole in right here, pointing from the partial positive region towards the partial negative region. Okay, and that dipole does not cancel out. There's no symmetry regarding the dipoles, and therefore it's a permanent dipole. It's a polar molecule. Okay, so what I want to do is I want to launch a poll question, and I want to ask you which of the following molecules is not polar? So think about these. You might want to grab some paper, and you might want to, I'm going to erase, draw out the Lewis structures. Okay, so you can look at this slide as well. And then we're going to go over this. Which of the following is not polar? And there should only be one correct answer.
Hey, Dr.
Again,
Evans.
oh, yes, question?
I was just wondering what the name of the slides are for today.
The ones we're going to go over for chapter 5 are called chemical reactions. The ones I'm looking at right now for this poll question are the molecular compound slides.
Thank you.
Huh, so far nobody's picking water. I wonder why. All right, we'll give it just a little bit more time. I'm glad we're going over this because we are getting wildly different answers. All right, probably 15 more seconds. So if you've not put your answer in, just throw it in and we're going to look at it in a minute. Okay, let's end this poll. Okay, I'm seeing in the chat, Alexis, what are you confused on this poll question? Are you confused on something else? Okay, well, I'm going to continue. So, all right. The 2 most popular answers were CH3. She said all of it. Okay. Well, maybe explaining it, what we're about to do, will help you walk through it. Okay. So the 2 most popular answers chosen right now were CH3Cl and CO2. Okay. Y'all said a lot of people thought either one of these is not polar, a non-polar molecule. So let's start with NH3 because some people chose it. So to assess these, you need to draw the Lewis structure out. So if you're trying to decide is a molecule polar or not, the best place to start is with the Lewis structure. And by now, I expect you to be pretty comfortable and pretty relatively quick with drawing Lewis structures. Okay, that's stuff we looked at with chapter 4. So I want you to be very comfortable with that. So if I'm looking at this and I say, 1, do I have polar bonds? 2, do I have lone pairs? 3, is it symmetrical? Can I draw in a partial positive and a partial negative? So remember, how do we decide if a bond is polar? Anybody remember? How do we decide if a bond is polar? It all has to do with electronegativity differences. Okay, so that was probably hard here, unless you had the chart, and I did not mention that. This chart right here, remember, we look at the electronegativity values and we calculate the difference. Simple math, addition, subtraction problem here. So if you're, I'm not going to take the time, but if you're looking at nitrogen, hydrogen, the difference is 0.9, and that is polar. Remember this chart as well, tells you if it's polar or nonpolar based on where that difference falls. Okay, so 0.9 means it is polar bond. So here in NH3, all of these bonds right here, all of these are polar. And so check, we got polar bonds, we got a lone pair, check on NH3. So we can write in the partial positives and partial negatives. What is the partial positives? These are the hydrogens. These are very electron deficient, okay? The electrons are going to be skewed or pushed towards the more electronegative element, which is nitrogen here, okay? So all these hydrogens, this is the electron deficient region of the molecule, and we can draw the partial negative up here on the nitrogen by the lone pair. Now, because of that, we have a separation, a little bit of charge, partial positive, partial negative. Now we can draw in a dipole pointing towards, or sorry, I meant to draw that, pointing towards the partial negative region, okay? And this dipole does not cancel, okay? So this is a polar molecule, all right? So a few people picked that, but most people, and then we talked about water. We actually, nobody picked water because we looked at that right up here. We said water, there's the partial positives, partial negatives. You can draw in the dipole, it doesn't cancel, okay? Some people might look at water and say, but it is symmetrical. If you draw a plane of symmetry right here, both sides are the same, but the dipole doesn't cancel, okay? The dipole is pointing one direction. If you drew it on this side, it would be pointing the same direction, okay? It doesn't cancel. Does that make sense? All right, let's go back down. So water, I'm not going to draw out water because we just looked at that. Okay, let's look at CH3Cl. A lot of people pick this one. So carbon's in the middle, and you got 3 hydrogens. It doesn't matter if your chlorine is up, down, right, or left, okay? So some of you may have drawn the chlorine pointing down or to the right. It doesn't matter. So we got 2 kinds of bonds here. We got carbon-hydrogen bonds, right? These are in red here. There's our carbon-hydrogen bonds. And we got a carbon-chlorine bond. And that one's right here. So 2 kinds of bonds. Remember, carbon-hydrogen bonds are never polar. Okay, so all of these bonds right here, these are non-polar. But this bond right up here, the carbon-chlorine bond, is polar. That's a polar bond. The electronegativity difference is 0.5, and that classifies it as polar. All right, and we got all these lone pairs, okay? All these lone pairs on chlorine. So if we were to draw in the partial positive, partial negative stuff, we draw the hydrogens as partial positive. The electrons are pulled towards chlorine. Chlorine is a very electronegative element. It wants to hog the electrons towards itself. And so this region up here would be the partial negative region. And we can draw the dipole in pointing towards the chlorine, okay? I like to draw the dipoles kind of out to the side. Okay, so does that make sense? So this is a polar molecule. CO2, that one we actually looked at. I'm going to scroll up because it's on the previous slide. Right here. CO2, you see the partial negatives and partial positives are already drawn in for us. We looked at this as an example in lecture. We got all these lone pairs, carbon-oxygen bonds. These are polar. These are polar bonds. And oxygen is very electronegative, so it's hogging the electrons towards itself. So we can draw dipoles in, but they are both going to be pointing towards the oxygen. And you see how there's symmetry right here in the middle? Draw a plane of symmetry. And so both of these dipoles, because they're pointing opposite ways, they cancel out. And because there's symmetry, even though you have polar bonds and lone pairs, and the dipoles cancel, this is a non-zero net polarity, non-polar molecule overall. So the correct answer here should have just been that CO2 is a non-polar molecule. Okay, so going back to those who said you were confused, does that help clarify? I'm going to ask, give me a thumbs up or a thumbs down. I'm going to click through on your screens right now. Thumbs up, thumbs down. Okay. Okay, good. Mostly I'm seeing a lot of thumbs up, but if this is still like you're lost on this, please stick around after lecture today or reach out to me via email if you can't stick around, and I'm happy to go over anything, okay? Let's jump into chapter 5 now. All right, we're going to continue with classifying chemical reactions. So I'm just going to get right into it. The first kind, there's 3 major kinds we're going to look at today. The first kind we're going to talk about is called precipitation reactions. I'm going to abbreviate precipitation reactions. You guys are familiar with what a precipitation is, okay? Or a precipitate, rather. It's a solid that forms when you mix 2 liquids. So this occurs when water soluble. What does that word soluble mean? It means something that can dissolve and stay dissolved in water. Okay, a water soluble reactants react to form 1 or more insoluble products. Okay, and the insoluble product here is the precipitate. So here's an example. We're mixing 2, you can see this picture over here. We're mixing 2 beakers, and these beakers have liquids in them. And you can see the moment they touch, the moment they mix, you get this really bright yellow compound. Okay, and it's kind of hard to tell. The compound doesn't look super solid there, but it's not translucent. You can't see through it, and that is a precipitate. Okay, so this picture is actually what's happening in this reaction right here. So let's read it. It's got PbNO3. What is that? That is lead nitrate. Again, I want you to be familiar with saying these. Lead nitrate. And notice it says AQ. Remember we talked about the abbreviations represent the physical states. What does AQ stand for?
Aqueous.
And that is something that is soluble. It's able to be dissolved, okay? AQ. Soluble is not abbreviated with an S, it's abbreviated with AQ. It's aqueous, it's able to be dissolved, okay? Same thing, you got lead iodide, or I mean potassium iodide. When these 2 mix, you create, your products are potassium nitrate. It is soluble, AQ. And then you got PbI2, and you see this abbreviation of an S. And remember, S here stands for solid. And a solid, a precipitate is a solid formed from the mixing of 2 liquids. So that, having this S right here, is the key indicator that that is your precipitate. So indicating the physical state on precipitation reactions is crucial. In fact, if you had all the abbreviations listed and you just look at it on the product, if you have something that is abbreviated with an S, that's a key flag, like a red flag or an alarm. Hey, this is a precipitation reaction, okay? So the lead iodine here, this is the PbI2, this is the precipitate. And then still in solution, you have KNO3 ions, potassium and nitrate, floating around, but they're dissolved and we can't see them, okay? All right, so this is an example of a precipitation reaction. So how do we know though, if let's say we didn't have any of the abbreviations, any of the AQ or the S indicating to us what kind of compound was what, soluble or insoluble? How do we know if something is going to be soluble and stay dissolved or if it's going to form a precipitate? Well, we can use this chart. It's called a solubility rules chart, okay? And this is going to tell us, it's going to allow us to look at any compound and then predict, is it going to be aqueous or solid? Is it going to form a precipitate or is it going to be dissolved in liquid? So the way you read this, anything over here in this column, I'm putting a box around this label here. Any of these, if a compound contains any of these ions, that compound is soluble. Okay, I'm going to say that again. If a compound contains any of these below ions, that compound is soluble. It is aqueous. Now you'll notice there are some exceptions, and that complicates things a little bit, and we'll get to those in a minute. But let's walk through this. The top 4 are cations. These are all cations. So if you have an ionic compound and the cation is one of these 4, ammonium, lithium, sodium, potassium, that compound is soluble. It does not matter what the anion is. Okay, if the cation present is one of these 4, and notice these 3 right here are all main group 1, main group 1. So a lot of the main group 1 elements are soluble, and there's no exceptions. Does not matter what it's paired with. All right, below are all your anions that are soluble. Okay, so if a compound contains nitrate as the anion, perchlorate, acetate. Remember, there's multiple ways to write acetate, by the way. On your lab, you saw it written as CH3COO. And here it's written CH3CO2. You may have also seen it written, someone told me that C2H3O2 is another acceptable way. Sorry, there's so many ways to write acetate, but it's all the same thing. All right, so if a compound contains acetate, it is soluble, no exceptions. The way this chart gets complicated is what I'm going to tell you next. If a compound contains these 3 halogens, chlorides, bromides, or iodides as the anion, it is soluble. Okay, so like sodium chloride, lithium bromide, that compound would be soluble unless the cation is either silver, mercury, or lead. Notice these are all transition metals. Okay. And think of it this way: you don't want to ingest any of these metals, right? You don't want sodium, or sorry, you don't want silver or mercury or lead in your body. So I'm kind of glad that it would not dissolve, right? We're kind of glad that these things would not be soluble. But anyway, so for example, if you have AgCl, here silver is the cation, chloride is the anion. Normally, a compound that contains chlorides would be soluble, but here, because the cation is silver, this would form a precipitate, a solid. S, remember, does not stand for soluble here, stands for a solid precipitate. All right, so that applies for bromide and iodine. These are the exceptions for these 3 anions. And then lastly, sulfate. Any compound that contains sulfate will be soluble unless the cation is barium, mercury 2, or lead 2. Okay, so for example, barium sulfate would form a precipitate, but sodium sulfate in a 2SO4, this would be aqueous. Okay, because sodium here is not an exception. What about calcium sulfate? Would that be a solid or aqueous? Would calcium sulfate be? Kendall says aqueous. Anybody agree or disagree? Keegan says aqueous. That's correct. This one would be soluble. That's a Q. AQ. Okay. All right, so does it make sense a little bit how to read this chart? Because we're about to do a practice problem with it. So I'm going to launch a poll question. I want to know which of these compounds, based on what we just walked through with the solubility chart, would be soluble in water. So these are lettered off A, B, C, D, E, and that's how I want you to think of it on the poll question. A corresponds to the CdCO3, cadmium carbonate. So you should be able to select multiple options here. I want you to click all that apply. Anything that will be soluble in water, click that. So remember, if it's on the chart, it is soluble unless there's an exception. Somebody make sure you're muted. All right, I think that's pretty good. I'm gonna go ahead and we're 80% voted, so get your vote in if you've not yet. All right, I'm gonna go ahead and stop it. And share results. Okay, so most people picked D and E. These were the two most commonly picked answers. Oh, it died. Which are soluble in water. So let's walk through these. Cadmium carbonate. If you look at the solubility chart, cadmium would be the cation here. That's not listed on the chart. Carbonate is also not on the chart. So that means it is not, so if it's not on the chart, it's not soluble. So that means it would form a precipitate, a solid. All right, so you don't want to pick A. Lead sulfate. Okay, I know sulfate's on the chart. That was the last one we talked about. But if the cation is lead 2, PbSO4, it will form a solid. Okay, so sulfate is soluble unless it's paired with barium, mercury, or lead. And here it is lead, so this will form a solid as well. So not soluble. All right, mercury 2 chloride. So chlorides are soluble unless it's paired with mercury 2. So that's also one of the exceptions. Okay, so Hg2Cl2, this is going to form a precipitate. All right, D, sodium sulfide, Na2S. Sodium is one of those main group 1 elements. And if it is the cation, that compound will dissolve, it will be aqueous. There are no exceptions. Okay, so it doesn't matter what the anion is. So this one you should have picked. That one will be soluble in water. And what about ammonium phosphate? Okay, so ammonium is the very first one. If it's on the list, it is soluble. All right, if it's on the chart, it is soluble. So no exceptions. It does not matter what the anion is here. Even though phosphate's not on the chart, you don't have to have both the cation and the anion on the chart. You just have to have one of the two pieces. Okay, so you should have picked these two. Questions on this one? Okay, how do y'all feel about precipitation? I think I got one more problem and then I'll ask you. So don't give me any response yet. Let's keep going. One more practice. So I want you to write the products here. What products will be formed? Are they soluble or insoluble? So we've got silver nitrate, aqueous, and we've got sodium carbonate, aqueous. When these two react, so you got to think, what kind of reaction is this? Is it combination, decomposition, single displacement, double displacement? What do y'all think? That's going to tell us how to predict the products. Is it combustion? Liana says, everybody says double displacement. So yes, this is a double displacement reaction. You got two ionic compounds. So remember, you got the cations here in blue. You got the anions in red. When you write your products, you have to have one red and one blue piece. You can't put the blues together and you can't put the reds together. Okay, so write your compounds and then go look at the solubility chart and see, okay, this is going to be aqueous or going to form a precipitate, and indicate that by writing AQ or S next to it. And make sure you write your formula correctly. So you need to write out the ionic charges here. So I'm actually going to start doing that. Silver. I noticed silver is paired with nitrate. Nitrate, we should know. Nitrate is a -1. That's a polyatomic. You guys should memorize that or know that. Silver is a +1 because you just have one cation here and it balances the anion. All right, carbonate is also a polyatomic, so we just have to know it's a -2. I got two sodiums here, so that means each one is a +1. All right, so keep those in mind when you write your compound. So the first compound you should have, somebody tell me, what did you write for the first compound? Or the first product? All right, several people are saying Ag2CO3. So we're going to pair up this one and this one. That's good. Ag, and we need two of them. Why do we need two? Because carbonate is a -2, and we got to write a neutral compound overall. So CO3. So 2 times the +1 on the silver here is going to give us total +2, and then this one carbonate is a -2, and that adds up to 0. And is this going to be aqueous or a precipitate? Based on our solubility rules, are silver or carbonate on that chart? When you go look at it, I don't remember seeing silver. Silver is here, but that's only because it's an exception for the halogens, okay? That does not mean it is soluble. That means it's one of the insoluble exceptions, okay? So silver is not on this side. This is your soluble side. So if it's not there, it's not soluble, all right? And carbonate's not either. So this one is going to form a precipitate. All right, next we should have, what was the other compound you guys wrote? NaNO3 is what I'm seeing in the chat. So we're going to pair up these two. So we got Na, you got to write the cation first, NO3. You just need one each because this is a +1, this is a -1. So one each, you get a neutral compound. And is this one soluble or aqueous? Sorry, is this one soluble, aqueous, or going to form a precipitate? All right, good. Seeing in the chat, a lot of people said this is going to be aqueous, and that is true because of both sodium and right here, sodium and nitrate are both on the soluble list. So they're present, so that's soluble for sure, 100%, no exceptions. All right, give me some emoji responses. Thumbs up, thumbs down. How do y'all feel with precipitation reactions and solubility rules? I love it when I don't see your head, but I just see this. That's good. Okay, good. Clicking through just to make sure. Okay, let's move on to the second kind. The second common kind of reaction is an acid-base neutralization reaction. Oh, I'm on highlighter. Acid-base neutralization reaction. For short, you can just call them acid-base reactions. Okay. Here's what I'm going to tell you. I'm going to give you a very narrow definition of an acid-base reaction. We're going to expand this much, much later when we get to chapter 10. So for now, this will suffice, but this is very narrow. So this commonly occurs between an acid, and the way we represent acids, we abbreviate them. HA stands for acid. So the H here stands for a hydrogen ion, and the A stands for acid. And the rest of the molecule here, the A part, this is actually the anion, okay? So the hydrogen ion is the cation part, and then the rest of the acid is your anion part, okay? So HA is how we abbreviate acids. Okay, so it commonly occurs between an acid and a metal hydroxide. So I'm going to abbreviate this M for metal, and then we know hydroxide is OH. OH minus, MOH. So this will yield water and a salt. Those will be the two products you get in an acid-base reaction. All right, so here's a very generic equation just underneath. HA, we see HA aqueous, so this is obviously the acid. And then we see MOH, this is the base. And if M stands for metal, let's think of some actual practical examples. What metal could we have? We could have some very common ones. You could have LiOH, this is lithium hydroxide. You could have NaOH, this is sodium hydroxide. Another example would be calcium, so that's a +2 though, so you'll need 2 hydroxides, CaOH2. These are all examples of really strong bases. Okay, and notice all these cations are metals. So you got HA and MOH. And then these are going to make water and a salt. So what's going to happen to the acid? Let's think. If this is aqueous, we know it's going to dissolve in water. And when it dissolves, you're going to get H plus and A minus, right? And this is the anion part, like we said. And then MOH, this is going to dissolve into your metal cation and your hydroxide anion. So this is going to look a whole lot, I mean, this is double displacement. Got two ionic things here. And your cations, oh, I meant to do highlighter. Your cations and your anions. Okay, so remember, you paired up blue and red, blue and red. So obviously, the H plus and the OH minus, those are what go to form your water. And then the metal and the anion part, those are what form your salt. Okay. So what we just are seeing here, so I'm gonna actually, these two are gonna go and form the water, and then put squares around these. These are gonna go and form the metal salt. So what we just kind of drew out, I'm gonna say in word form now, right here. The hydrogen ion from the acid, we just see that it's going to combine with the hydroxide anion from the base, and that's what gives us neutral water. So we call it a neutralization reaction because we form a neutral compound, water, or a molecule. And the anion from the acid, okay, that's the A minus part right here, is going to combine with the metal cation from the base, and that gives a salt. So again, this is double displacement. So if you see water as a product, if I give you a reaction, I say, what kind of reaction is this? Is it precipitation, acid base? We're going to look at redox next. What kind is it? If you see water is a product, that's a good indicator that it's acid base. Let me give one clarifying thing though. It's so hard in chemistry to make generalizations because there's always exceptions. One I can think of right off the bat, combustion reactions. If I give you a combustion reaction, we know that we said there's always two products on a combustion reaction, carbon dioxide and water. Okay, but a combustion reaction is not an acid-base reaction, okay? So if you recognize it as a combustion reaction, do not also classify it as an acid-base reaction, okay? Even though water is a product, all right? So if water is a product, it's usually acid-base, but if you immediately recognize its combustion, it's not an acid-base reaction. All right, I want you to write the products for this reaction down here, the red and the black. This first thing, CH3COO, you should recognize that as an acetate anion. And when you put a hydrogen on it, it becomes an acid. This is acetic acid. Anybody ever messed around with vinegar or use it to cook or whatever? The acid in vinegar is acetic acid. So you can imagine how that smells. It smells like vinegar. So you got acetic acid and you got sodium hydroxide. So this is your acid and this is your base. And the portions of these molecules are already color-coded. So I want you to write the products based on that. Take the red pieces and put them together. Write cation first, anion second. So obviously we should know one product is going to be water. And that's the black portion. And then the other part will be sodium acetate, Na, CH3, COO. And remember, there's multiple ways you can write acetate. And this will be aqueous as well. Okay, questions on acid base. We're going to work one problem together. But questions right now on anything from this slide. Okay. So let's do a practice problem. Write and balance the equation for the following acid-base neutralization reaction. Cesium hydroxide and hydrogen sulfate. Cesium hydroxide. So here I'm actually wanting you to write out the formulas for your reactants as well. See, so you're gonna need a periodic table probably. Anybody want to tell us what is the abbreviation for cesium? Cesium. It is in main group 1. Thank you, Summer. It's CS. CS. It's in main group 1. So what charge would it have as a cation? +1. It's going to be a +1. And then we know hydroxide is a polyatomic. It's OH minus. So how many cations and how many anions do you need to write this? So you should just need CSOH. Okay, and then hydrogen sulfate. How do we write hydrogen sulfate? So obviously we got hydrogen, that's going to be a +1. Sulfate is SO4 -2. Oh, I forgot to cross that. Keegan says H2SO4. Anybody else? That's correct. You need 2 cations for 1 anion here. All right, so which one's your acid? Which one's your base? First off, which one's the acid? That's right, H2SO4, this is the acid. And then the metal, you should have recognized this is a metal, and then OH, we said that's the base. All right, so this is double displacement reaction. So we got our cation, I always do this. Cation, no, I wanted blue. Cations, anions. I'm really good. The one part I'm going to miss when we go back to face is like writing on this iPad. There's so many features. Like I like the highlighting part. How many of you are ready to be back face to face in classes? How many of you are like, no way, I like online? I don't know, people feel different ways. Personally, I'm ready to be back in the classroom. That's me. All right, so what products do we get? You should match up cations and anions. So you obviously, oh my goodness. H2O, and then you should have CS, and this is, how many cesiums do we need? It's going to be cesium sulfate. You're going to need 2 of them to balance that SO4. Okay, so these are the products you should get. It doesn't look like it's balanced, so you could go back and balance it. You'd need a 2 there, and I think you'd need a 2 there. But that's acid base, okay? You made water and you made a salt. Okay, questions for acid base? All right, we're going to move on to the third one if there's no questions so far. All right. Okay, third type of reaction. I'm actually going to pause and intro this for a second because this reaction type is maybe a little more complicated to understand. I don't know. I don't want to give it a bad rep, but this reaction is so vital to us, these reactions. So I wanted to show you some pictures of some devices that are pretty life-altering devices and impactful things. So my question here, besides what are these things in these pictures, is what do they have in common? So first off, what kind of pictures? What do you see in the pictures? What kind of devices are these? Can anybody tell me one of them? Pacemaker. Okay, Bailey says pacemaker. Someone says a hearing aid. Hearing aid. Yeah, so it's actually, Summer said, it's actually called a cochlear implant, but it works very much like a hearing aid. But it's different from a hearing aid because it is injected also, it's got a piece that injects into your brain. So hearing aids don't quite do that. So we got a pacemaker right here. And then we got a cochlear implant. Okay. And then down here we have, I don't know the actual medical term for it, but it is some sort of device that's going to help with things like PTSD. Okay, so that's why you see a guy in a army suit there. But it's kind of a brain implant that will help with people who maybe you know somebody that has dealt with PTSD, and that can help. But that's a pretty big decision to get something injected in, like that's a permanent part of your brain. Okay. But what do these things do? They obviously help people in a lot of ways. Cochlear implants take auditory signals. So for people who cannot hear well or maybe deaf, they take auditory signals and they then transmit it so that they can actually help hear verbal things and process speech. Pacemakers help with our heart. They help keep it in rhythm. My grandfather was in the hospital a couple years ago with congestive heart failure, and they had to make a decision. Do we want to try to put a pacemaker in or just give him medication to keep his heart in rhythm? And he's in his 80s, so they decided pacemaker and surgery was not the route for him. But these are very helpful for a lot of people who have issues with their heart. But what do these things have in common? What are these devices? Yes, they're small. Yes, they're medical devices. But at the base root of them, can anybody think?
All dealing with like neurology.
They do all interact with your nervous system, Hunter. That is true. But I like what Bailey said. She's kind of getting more at it. Electricity. They all have small batteries. Okay. They all have small batteries. And the reason I wanted to bring up batteries in a health science related way is because that is essentially batteries depend on redox reactions. Okay. And think about how much our life depends on batteries. How many of you, your phone runs out of battery at 10 a.m.? Our life depends on batteries. If we did not have batteries, then we don't have life as we know it. So batteries are run on redox reactions. So I really do more than just knowing all the ins and outs of redox reactions. I want you to walk away today with an appreciation for chemistry and how it interacts with your life every day, whether it's in a medical sense or not, because of redox reactions. So the redox is an abbreviation for oxidation, reduction, reactions. Oxidation, reduction, reaction. So there's two parts here, and we're going to look at both parts. What is oxidation and what is reduction? But in short, the kind of most blanket statement I can give you or definition I can give you is that a redox reaction is one in which electrons are transferred from one atom to another. And I want to pause here because you actually are very, very, very familiar with the transfer of electrons, right? That was all when we learned cations and anions, we learned that electrons are transferred and how that leaves atoms with a plus charge or a minus charge, okay? So just remember, you're familiar with this. You know all about valence electrons and how they're transferred. But let's break down the two words, oxidation. Okay, so oxidation is when an atom loses an electron. That's like when we learned how things become cations. The way oxidation, though, is different from forming a cation is that it doesn't mean something becomes positively charged. Not always, at least. Certainly, something turning into a cation, that is oxidation, but look at this figure. This is from your textbook. If you read this figure from left to right, left to right, let's look at the very first one up here. You have something with a -2 charge. If it loses an electron and it becomes something with a -1 charge, the charged increase from -2 to -1. That is oxidation. It is losing an electron, right? Now, did it become a cation? No, it did not become positively charged, but it was oxidized. So you see the difference between oxidation and just something becoming a cation? It can be a little more broad. Same idea, if something has a -1 charge and it loses an electron, now it has no charge. Okay, now the number of protons and electrons in that atom are again equal. All right, so that's oxidation, and you could go on and on and on. Okay, reduction is the gain of one or more electrons. Okay, so if you read this figure from right to left in reverse order, let's start down here at the bottom. If we have an electron and we add it to this element right here, it has a +2 charge. If it receives an electron, remember electrons have negative charge. So where electrons go, negative charge goes. So if it receives a negative charge, now it's only a +1 charge. The charge was reduced from a +2 to a +1. That's reduction. Okay, what about if you have a +1 charge and you add another electron? Now you're neutral again. Does that make sense? So if you read all these figures from right to left, that's reduction. If you read them from left to right, that's oxidation. So oxidation and reduction are opposite of each other. I want to introduce this phrase oil rig. Maybe you've heard it before. This is a great way to memorize oxidation reduction, because I promise half of you are going to be like, oh crap, gaining electrons. I don't remember. Is it oxidation reduction? Well, if you think oil rig, you'll remember. Oil rig stands for oxidation. I'm going to abbreviate. Is the loss of electrons, OIL. And when that happens, your charge increases, okay? I'm not saying you become positively charged, but your charge does increase. Okay, reduction is the gain of electrons, so RIG. And when that happens, when you gain an electron, your charge decreases, all right? So maybe that will help you keep it straight. All right, where this gets complicated and nuanced is we're going to now apply this to the context of a chemical reaction, a real one. We're going to look at a real example, and we're going to try to identify what element is losing electrons here and what element is gaining. You can very, very much think of this similar to the way you would assign ionic charges. And you would ask yourself, is this a +2 or a +1 or a 0? I want you to remember right now, anytime you have a neutral element, like an element written by itself, that is charge neutral, right? And before it interacts or becomes part of a compound, we always say elements by themselves have the same number of protons as they do electrons. And in that sense, they are charge neutral. So remember that, because we're about to go in and try to assign charge numbers. So let's look at this reaction with copper. Cu is copper, and we have copper, elemental copper by itself. It's just solid metal copper. And it's reacting with silver nitrate. And notice that is aqueous. That's a compound, ionic compound. The questions here are what happens to copper and what happens to silver? Well, as they react, notice that we end up with solid silver by itself, and we end up with copper nitrate. So first off, what kind of reaction is this? Is this a combination, decomposition, single displacement, double displacement? Anybody recognize it? Haley says single displacement, That's correct. We have an element and we have an ionic compound. When you have one element and a compound, remember that that element is a metal, metals replace cations. If it's a non-metal, non-metals replace anions. So here we have a metal, copper, and it's going to replace the cation, which is silver. And so essentially, copper and silver just switch. So it's a single displacement. So let's answer these questions right here. What happens to copper? I want to know, like, charge-wise, what happens? If you had to assign a number to copper that was indicative or kind of alluded to what charge it has right now on the reactant side, what number would you give it?
-2.
-2. Okay, why -2?
It might be +2.
Okay, so right now as an individual element, okay, I'm seeing in the chat 0. Okay, Jonathan, in a compound, yes, it would have a +2 all day long, okay? But it's by itself right now, okay? So anything that's by itself is going to be a 0. So copper right now has no charge. It's just natural, neutral copper. Okay, what about silver? What would you give it? It's in a compound. It's a cation in this sense. What would you give silver? If you're not sure, look at the anion. We've got nitrate. What charge does anion carry? Or sorry, nitrate carry? This is a polyatomic, so we got to know the charge on this. Nitrate is a -1, and we only have one of them, so the total magnitude of negative charge is -1. Remember, this is a neutral compound overall. That means the positives and the negatives add up to 0. So that means silver must be a +1 here. +1 and -1 add up to 0 total. Okay, so starting out, we've got copper is 0. And starting out, we've got silver is a +1. What happens on the product side? What number would you give silver on this side to allude to any charge that it does or does not have? Okay, I'm seeing in the chat, people are saying 0. Does that make sense though to you? It's by itself, it's an element, it's not in a compound, so it's neutral. Okay, what about copper? What number would you give copper here? Jonathan, now's your time to shine.
Oh my gosh, it'd be +2.
There you go. Okay, we got 2 nitrates this time. Remember, nitrate's still a -1. Okay, nitrate doesn't change, by the way. It's a -1 on both sides, so we're not concerned with nitrate. Okay, so silver goes from +1 to 0. Copper goes from 0 to +2. So the question, what happens to copper? Is it oxidized or is it reduced? It goes from 0 to +2. Go back to oil rig. Did it gain or did it lose electrons? Goes from 0 to +2. Seeing different things, oxidized or reduced. So it lost electrons, which means, we go back to our thing, anything that loses electrons, that's oxidation. So copper is oxidized. And that's exactly what you see if you're looking at this red and blue label stuff down here. Started out with 0 charge, it becomes a +2, so it lost 2 electrons. This is oxidation, okay? Silver is going to be the opposite. Silver was reduced in charge. It was a +1, then it went down to 0. So this is reduction. So copper is oxidized, silver is reduced. And that's exactly, if you were noticing the things down here, it's a +1 on the reactant side, it's a 0 on the product side. And so it gains electrons. Now notice there are 2 silver atoms, okay? You see the coefficient of 2? Each silver picks up 1 electron, okay? So copper gives 2 electrons away, 2 silver atoms, each individually pick up 1 electron, okay? Okay, so, and then there's a picture of it over here. We've got this copper wire in the solution. We have the silver nitrate, and this is the copper. And then what do you see over here? Looks like a bunch of stuff is growing on the copper wire, and it is. This is silver. And then you notice how the solution looks blue. This is copper nitrate. Anybody has seen copper turn colors before when it's kind of weathered? My husband thought it was a good idea to get a copper wedding band. His first, like his very first wedding band was a copper one. He'd wash his hands all the time, and it's literally his finger. It was kind of gross, so he got a different one, but it turned green or blue. So that's what copper does to solutions. It kind of turns like a greenish bluish color. All right, so redox reactions. How many of you agree with this statement? They're usually straightforward. Do y'all think they're straightforward? No. They are not necessarily straightforward, but when you understand oxidation and reduction at the basic level, you can always find something that is increasing in charge, something that's decreasing in charge. So you're looking at the change in charge, right, to determine which compound is oxidized and which one's reduced. So right now, give me some thumbs up or some thumbs down. How are y'all? This is new, so I don't expect a ton of thumbs ups. Thumbs up. Are y'all okay? Y'all hanging with me? I know we've been going for a while, so I see some kind of eh. All right. Well, the more we do this, hopefully the more comfortable you will become. Here's another one. Let's look at this one really quick. I would love for you to, down here, fill in the blanks on these. So you have potassium iodine, and then you have elemental bromine, which is an element by itself. And that's going to react. It's a single displacement again. But this time, bromine is not a metal, it's a nonmetal. And remember, nonmetals displace anions. So bromine is going to kick out iodine, and replace it. So you're going to end up with potassium bromide and then iodine by itself. So if you're looking at what happens to the charges here, starting out, iodine in the compound, if we had to assign it a number, it'd be a -1, right? It's like the anion here. But by itself, when it's by itself on the product side, it has no charge, it's neutral. So it changes, it goes from a -1 to a 0. And that's exactly what you see down here. Iodine ion is blank. It does what? Is it oxidized or reduced as its charge increases from -1 to 0? Does it pick up electrons or lose them? Think about that. Remember, electrons carry negative charge. So if you gain electrons, you're reduced. But if you lose electrons, okay, I'm seeing it in the chat, it's oxidized. Right? It increases from -1 to 0. So bromine, on the other hand, starts out as 0 because it's by itself, so 0 charge on the reactant side. But in the compound KBr, it's the anion. It's a -1. So it goes from 0 to -1. So we say it was reduced. So we walked through that a lot quicker than the previous slide, but still the same steps here. We're still looking for things that are by themselves, and then we're looking at what kind of charge things carry in a compound. All
I
right.
have a question.
Yes. Danielle.
Okay, so the whole like if it's neutral or not, does it matter? Like how you said on this one it was on the product side, but on the last one it was on the other side. So like it can be on either side.
Okay, I'm not sure I understand. Say that again, Danielle.
Okay, so on this problem, you said how the neutral one it has like no charge or whatever. It's like neutral.
Right. So bromine here is 0.
Uh-huh.
Uh-huh.
Oh, okay. Because I was looking at it kind of at the
You're going to have
oh,
something. We've had something that's neutral on both sides. So up on this
okay.
first slide, it was copper that was 0. Now, yes, it was listed as the first element. That doesn't matter if it's written first or second.
Okay.
Is that what you're getting at?
Yes.
Yeah, here bromine's written second. That doesn't matter.
Okay.
Okay, great question. So what we've been doing, without me even telling you this, because you're drawing from previous knowledge of ions, cations, and anions, we have been assigning what we call oxidation numbers. And these are very, very similar. It's so easy to think of oxidation numbers as charges, because in many cases, the oxidation number matches the charge something would have as an ion. But what are they? And if I could, before I define it, if I could beg you, if I could implore you to read 2 pages of your textbook, okay? I don't know if you've been keeping up with the readings. If you have, great, you should. But if you've not been, this is page 151 and page 152. Please, 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 right after lecture, if you have time or sometime today, just go read these 2 pages. It will take you all of 5 minutes. And this will help just kind of, I think, put a seal and help confirm a lot of the things we're talking about and give you good examples of oxidation numbers. So what are oxidation numbers? We've been assigning them. That's the numbers, the charges we've been writing on things. They are numbers we assign to atoms to indicate if they are electron rich, electron poor, or neutral. So obviously, if it's a 0, it's neutral. If it's gaining electrons, it's becoming electron rich. If it's decreasing or increasing in its charge, it's becoming electron poor. But there is a difference, okay? Even though they feel a whole lot like charges, ionic charges, they do not necessarily imply ionic charges. And this is where the book is going to help clarify, because what I'm saying probably sounds very vague. But there's some rules when we assign all these numbers up here, like we've been doing with the copper and the everything else and the silver, all these numbers that we put in, these are oxidation numbers. And here's the rules. If you ever have a question on what number do I give what element, rule number 1, an atom in its elemental state by itself, not in a compound, has an oxidation number of 0. And that's what we've been doing with copper. And when it's by itself, we give it 0. Okay. Number 2, a monatomic. What does that mean? It means an ion by itself. So if you're considering an ion by itself, monatomic ion has an oxidation number equal to its charge. All right, equal to its charge. There's certain atoms and certain elements that will always have very predictable oxidation numbers because they have predictable ionic charges, okay? And those are main groups. I'm going to draw an arrow here. What's predictable are main groups 1 is predictable, main group 2 is predictable, and then main group 6 and 7. Elements in those main groups. So cations like sodium and lithium and calcium and magnesium, anions like oxygen and sulfur and your halogens. The oxidation numbers you give them will always match their charges as an ion. A +1, a +2, or a -2 or -1. Okay. Now in a compound, rule number 3, an atom usually has the same oxidation number it would have if it were an ion. That sounds very repetitive, and it is. So if you're looking at a compound, which is what we did up here with, let me scroll up, like KBr, okay? When we were trying to think about these earlier, and we said, well, potassium is a +1, and say bromine is a -1, you're thinking about what kind of charge it would have if it were an ion, okay? And it's an ionic compound. So that's what rule 3 is getting at. Rule number 4, it says the sum of oxidation numbers in a neutral compound. Remember, all ionic compounds, when you put the cations and the anions together, those are neutral overall. Everything, all the charges add up to 0. And it's the same with oxidation numbers. The sum of oxidation numbers add up to 0. Your book walks you through an example of HNO3, and I'm just going to draw it out really quick right now. I know we have very little time left. Looks like this. I'm not going to get all the bonds right now. I'm just going to connect the atoms. So you'll see different bonds in your textbook. It's got a lone pair on it. If we had to go through and assign oxidation numbers, I would tell you to assign the elements that you know first. Okay, so the ones you should know in a compound are anything in main groups 1, 2, 6, or 7. Those are the ones that are going to have predictable oxidation numbers. So I know hydrogen's main group 1. So I'm going to give it a +1 because everything in main group 1 is always a +1. Oxygen's main group 6. So I'm going to give that a -2. All of those, each of those have a -2. So if the sum of these numbers have to add up to 0, what oxidation number would we give nitrogen? If the sum of all of these charges we just wrote in are oxidation numbers, I'm seeing in the chat, everybody's writing +5, +5. And that feels very bizarre. Usually nitrogen as an anion carries a -3. But this kind of reinforces the point that oxidation numbers don't always match charges. Sometimes you see weird things like nitrogen here being a +5. Okay. All right, so again, go read those 2 pages. It should help walk through everything we just said with these rules and give you some really good examples. All right, questions on oxidation numbers. We're about to do one practice. We only have 3 minutes left and then we're done. And if you have questions, I'll stick around afterwards.
What are the page numbers again?
151 and 152. 151 and 152.
Thank you.
Uh-huh. Okay, one practice, and then that's all we have time for today. In the following reaction, which element is oxidized and which one is reduced? Tip, start out assigning oxidation numbers. So if I give you a reaction, I say, is this precipitation? Is it acid-base? Is it redox? If you recognize that it's not precipitation and that it's not acid-base and you're thinking, oh, maybe it's redox, go through and assign oxidation numbers. So really quickly on the reactant side, what oxidation numbers would you give silicon and chlorine? They're elements by themselves. They're elements by themselves. Yep, that corresponds with number 1. An element by itself should be a 0, 0. Okay, and then on the product side, we have SiCl4. we have to assign an oxidation number to silicon and to chlorine, and the sum of those things, remember we got fluorochlorine atoms in this compound, they have to add up to 0. That's rule number 4. And you always list the element with the positive oxidation number first, the element with the negative oxidation number second. Just like ionic compounds, you write the cation first, anion second. So what oxidation number do we want to give silicon? Okay, Matt offers a +4. Let's just go with it. Let's just see. And then chlorine, if we're going to give silicon a +4 and we got 4 chlorine atoms and this has to add up to 0, what should we give chlorine? An individual chlorine, 1 chlorine. Okay, Lucy says a -4, other say -1, Kishan and Maddie say -1. -1 seems to be the common answer here. Total, Lucy, it does add up to, or multiply up to be -4. Okay, you got 4 of them, so technically, yes, that's 4 times -1. And the -4 and the +4 balance out, but the actual oxidation number we're going to give one individual chlorine is a -1. Okay, so we're at time, but really quickly, Si goes from 0 to +4. Cl starts out as 0 and it goes to -1. So if I ask you, what is oxidized, what is reduced? Remember, oxidation is the loss of electrons, charge is increasing. So silicon is oxidized. It increases. Chlorine is reduced from 0 to -1. So we say it's reduced. Okay, that's it. I'm done. Questions? You can stick around. There's another practice problem if you want to look at that and attempt that on your own. Remember the bonus point opportunity. Remember your quiz today. Oh, why didn't anybody tell me to stop sharing the poll?